Welcome back to Bite-Sized Breakthroughs, your weekly dive into the latest advancements in the world of artificial intelligence. Today, we're exploring a fascinating research paper that challenges our understanding of how neural networks learn. Joining us is Dr. Paige Turner, a leading researcher in the field, and Professor Wood Spectrum, a renowned expert on the broader context of AI development. Dr. Turner, can you introduce us to the main topic of your paper?
Certainly, Alex. The paper titled The Lottery Ticket Hypothesis Finding Sparse Trainable Neural Networks investigates a fundamental question in deep learning. Why do we need such massive, overparameterized neural networks to achieve high accuracy? We found that these large networks actually contain smaller, sparse subnetworks that are surprisingly capable of learning on their own, potentially rendering the overparameterization unnecessary.
That's a very interesting starting point. Professor Spectrum, could you provide some historical context to this debate about overparameterization in neural networks?
Well, Alex, the practice of using networks with far more parameters than strictly necessary for a given task has been prevalent in deep learning for a while. This is largely because we found that overparameterization often leads to better training outcomes. Previous research has demonstrated that pruning techniques, which involve removing unnecessary connections and weights from a trained network, can significantly reduce the number of parameters without harming accuracy. This suggests that a lot of the parameters might be redundant. This paper takes it a step further by exploring the possibility of training these sparse networks from scratch, rather than just relying on retraining pruned models.
Dr. Turner, how did you approach this investigation of sparse, trainable subnetworks? What are the key contributions of your research?
Our approach was based on a new hypothesis, which we call the lottery ticket hypothesis. It suggests that randomly initialized dense neural networks contain subnetworks, which we refer to as winning tickets, that are exceptionally well suited for training. These winning tickets possess a fortuitous combination of weights and connections that make them capable of learning efficiently. We used a standard neural network pruning technique to uncover these winning tickets. The key innovation is that we not only prune the network, but also reset the surviving weights back to their original initializations after each pruning iteration. This iterative process helps identify progressively smaller trainable subnetworks that maintain comparable performance to the original network.
So you're suggesting that these winning tickets are essentially born with the right set of parameters and not just molded by the training process.
Exactly, Alex. We found that the initializations of these winning tickets are critical for their success. We demonstrated this by randomly reinitializing the same subnetworks after pruning. These randomly reinitialized versions performed significantly worse than the winning tickets with their original initializations, highlighting the crucial role of initialization in their effectiveness.
Professor Spectrum, how does this concept of winning tickets fit into the larger context of neural network optimization?
It's a fascinating concept, Alex. It challenges the conventional view of neural network optimization. We've often attributed the success of deep learning to the fact that we have massive networks with a vast parameter space, allowing optimization algorithms to find good solutions. The lottery ticket hypothesis suggests that this overparameterization might not be essential, and that optimization might be implicitly searching for these pre existing, well initialized subnetworks. This idea connects to recent research exploring the role of overparameterization in deep learning. It suggests that overparameterization might not be necessary for achieving good accuracy, but rather it increases the probability of finding these winning tickets.
That's a really thought-provoking idea, Professor Spectrum. Dr. Turner, let's dive into the methodology you use to identify these winning tickets. Could you describe the iterative pruning process in detail?
Sure, Alex. We used a standard neural network pruning technique where we iteratively removed the weights with the lowest magnitudes. After each pruning step, we reset the remaining weights back to their original initialization values. This is what we call iterative pruning with resetting. We compared this with another approach, iterative pruning with continued training, where we simply retrained the network with the surviving weights after pruning. Our experiments consistently showed that iterative pruning with resetting was more effective in finding smaller, trainable subnetworks that matched or even surpassed the original network's performance.
So, resetting the weights to their original values after each pruning step seems crucial for finding these winning tickets. Could you elaborate on the rationale behind this approach?
It's important to consider that the initial weights are not random noise. They are drawn from a specific distribution, and they inherently hold some information. By resetting the weights to their original values, we are essentially giving the network a fresh start for training, allowing it to explore the parameter space in a way that is more aligned with its initial configuration. This seems to be crucial for identifying winning tickets, as they are likely to be sensitive to their initial configuration.
That makes sense. Dr. Turner, can you tell us more about the specific experiments you conducted and the results you obtained?
We conducted a series of experiments using various neural network architectures, including fully connected networks like Linnet and convolutional networks like COM2, COM4, COM6, VGG19, and ResNet18. We evaluated the networks on two common datasets, MNIST and CIFAR10. In all these experiments, we consistently found winning tickets that were significantly smaller than the original networks. For instance, on a fully connected network for MNIST, we found winning tickets that were less than 10% the size of the original network, while for convolutional networks on CIFAR10, we found winning tickets as small as 20% the original size. These winning tickets consistently achieved comparable or even higher accuracy than the original network, sometimes even learning faster and generalizing better. This was a key finding, as it challenged the notion that larger networks were necessary for achieving good performance. We also explored the interaction between dropout and iterative pruning, finding that dropout, which randomly disables units during training, can actually enhance the effectiveness of pruning in finding winning tickets. This suggests that dropout might prime networks for pruning by introducing sparsity during training.
These are impressive results, Dr. Turner. Professor Spectrum, what are your thoughts on the implications of these findings?
The potential implications of this research are profound, Alex. It suggests that our current approaches to training and designing neural networks might be unnecessarily complex. If we can effectively identify and utilize these winning tickets, we could potentially train more efficient models that are smaller, faster, and more resource-friendly. This is crucial for deploying AI models on devices with limited memory and processing power, like mobile devices or Internet of Things, IoT devices. Furthermore, the discovery of winning tickets could inspire new network architectures and initialization schemes that are specifically designed for sparsity, potentially leading to more efficient and robust AI systems.
That's incredibly exciting, Professor Spectrum. Dr. Turner, do you have any thoughts on the limitations of your current research and what directions you see for future exploration?
Certainly, Alex. Our research has focused on relatively small data sets and vision-centric classification tasks. We need to explore the lottery ticket hypothesis in more complex settings, such as those involving larger data sets like ImageNet. This requires more efficient methods for finding winning tickets, as the iterative pruning technique we used is computationally expensive. Another limitation is that we primarily focused on unstructured pruning, which might not be optimal for modern hardware and libraries. We need to investigate the use of structured pruning techniques, which could potentially produce more efficient and hardware-friendly architectures. And finally, we need to delve deeper into the properties of these winning ticket initializations to better understand why they are so conducive to learning. This could lead to novel initialization schemes that are specifically designed to identify and exploit winning tickets.
Those are all very important points, Dr. Turner. It's great to hear about the exciting avenues for future research. Professor Spectrum, do you have any final thoughts on the broader impact of this research?
The lottery ticket hypothesis, if confirmed to be a general phenomenon, could fundamentally shift our understanding of neural network design and training. It might lead to a complete rethinking of how we design and train neural networks, potentially resulting in a new era of more efficient and accessible AI applications. Beyond its immediate impact on deep learning, it also has implications for other areas, such as theoretical computer science, computational neuroscience, hardware design, and even AI ethics.
Thank you both for sharing such insightful perspectives. Dr. Turner, we appreciate your groundbreaking research, and Professor Spectrum, your expertise in placing this work within its broader context. This has been a fascinating exploration of the lottery ticket hypothesis, highlighting a potential paradigm shift in the field of deep learning. As we've discussed, this research has the potential to significantly impact the development of more efficient, robust, and accessible AI systems.
Thanks for having us, Alex. It's been a pleasure discussing this intriguing research.
It's been a great conversation. Join us next week for another bite-sized breakthrough.